Hello, everyone, and thank you for joining us for today's Würth Electronic Power Webinar, Migration to USB-C, Meeting EMC Standard, Effective Power Protection, and High Interoperability. Today's webinar is presented jointly by Würth Electronic and ST Microelectronics. Our first presenter is Jeff Hallio, Product Marketing Engineer with ST Microelectronics. Our second presenter is Apurva Ingle, Product Definition Engineer with Würth Electronic. Assisting with questions at the end is Quentin Ledebert, Team Leader for Product Definition Engineers in the Americas with Würth Electronic. Today's webinar is, of course, powered by our exclusive sponsor, Digi-Key Electronics. You can find Würth Electronic components online at digikey.com. If you have any questions during today's webinar, feel free to ask them in the questions box, and our presenters will answer them at the end. If your questions do not get answered or you think of them a bit later, simply email us at hereforyou@we-online.com. As a reminder, because you registered for today's webinar, you will automatically receive the presentation slides and the video on demand when they become available within the next 24 to 48 hours. Don't forget to register for our next webinar, Function and Design of Coaxial Connectors. Now, please enjoy today's Power Webinar, Migration to USB-C, Meeting EMC Standard, Effective Power Protection, and High Interoperability.
Hello, I'm Jeff Hallio, a product marketing engineer for the General Purpose Analog Division at ST Microelectronics, based in the Burlington, Massachusetts office. I have product responsibility for the USB-C with power delivery controllers. Here's the agenda for today. I'm going to quickly provide an overview of USB evolution. Next, I'll explain the paradigm change and motivation from people and companies to migrate to USB-C universal charging. I will then highlight migration risks and protection concerns, and then finally I will share design guidelines for a clean implementation on the sync side in order to guarantee both safety and interoperability. So starting with USB history. First released in 1996, the USB standard is maintained by the USB Implementers Forum. Starting with USB 1.x, which defined 1.5 megabit per second data rate for low speed and 12 megabit per second for high speed, the initial release accomplished many of the initial objectives, including self-configuration and hot swappable capability, and the replacement of the many connectors on the back of a PC with Type A host-side connectors. In 2001, the USB IF ratified USB 2.0, which increased the data rate to 480 megabit per second. We also witnessed the introduction of mini and micro connectors for the device side of the cable to replace the larger Type B connectors, and this was an important development for space-constrained portable devices. In addition, the on-the-go supplement made it possible for two USB devices to communicate with each other without requiring a separate USB host to coordinate. The USB 3.0 specification was published in 2008 with the main goals of increasing the data rate up to 5 gigabit per second, decreasing power consumption, while increasing power output available to the connected devices, and also maintaining backward compatibility with USB 2.0. USB 3.0 accomplished these goals by including a new higher speed bus called SuperSpeed, which maintains the slower data rate USB 2.0 bus in parallel. So if you examine a USB-C connector, you'll notice pins dedicated to the USB 2.0 signals, as well as two high-speed differential lanes on separate pins. A few years later, the USB 3.1 specification again bumped the high-speed data rate to 10 gigabit per second. And finally, in 2017, with USB 3.2, the data transfer capability was increased again to 20 gigabit per second, although this was done by increasing the number of lanes that were dedicated to the high-speed data transfer, rather than by increasing the actual data rate of the lanes. From a power perspective, USB has always been a 5-volt bus, up to and including USB-C, which supports by default 5 volt at 3 amp, equal to 15 watts of power. With the addition of USB-C with power delivery, that power capability has been expanded up to 100 watts of power, with a 20 volt bus driving up to 5 amp of current. Recently, we have seen some press releases about the USB Extended Power Range optional layer, which will support 48 volts at 5 amp, equal to 240 watts of power. That extension is mainly being driven to address PC applications, where 100 watts was not quite enough to quickly charge a laptop battery. It's still pretty early in the EPR development, but ST has a presence in the USB working group, and we will be ready to provide controller and power solutions once that market develops. Following that brief history lesson, we'll move on to the market trends. So the market is evolving. There are plenty of portable battery-powered devices with different power capacities that need to be charged quickly, anywhere, at any time. Carrying many kinds of AC adapters is a mess. There's always one missing, and the young connected generations are looking for simplicity and portability, but they're also sensitive to their environmental footprint. This is why 100-watt universal charging based on USB-C can cope with both the charging technical requirements as well as the expectations and way of life for the younger folks. To achieve this, the industry is innovating and is working on replacing external AC adapters, which use custom connectors, with a simple USB-C cable. On the sync side, which is our focus today, custom power plugs, which support far below 20 volts at 5 amp, as well as USB micro B plugs, can both be replaced by a unique USB-C connector. This means that all micro B devices will sooner or later migrate to USB-C, but also that non-USB products are now eligible to migrate to universal charging as well. That's why USB-C is such a game changer. On the source side, all new chargers in the computer and smartphone industry are now developed with USB-C connector. And the challenge today is to increase the power density or to integrate the AC to DC power conversion into the walls, using GaN technology, for example. There are several different reasons which are pushing organizations to adopt USB-C, as illustrated by this communication from the USB Implementers Forum. Reusability and sharing of chargers, electronic waste reduction, improved user experience, but also local legislation with governments worldwide moving in this direction. On the technical side, there are also many sources of motivation for designers. For existing micro B devices, getting more current or more power allows for faster charging or to increase battery capacity or gain efficiency. For custom power plug applications, adopting a standard connector improves the product design and user experience. And for AC power devices with a captive cable, there's also an opportunity to move away from the heavy AC to DC conversion to a more effective DC to DC power management. This chart is to let you know that ST is meeting at the board of directors together with leading actors from the industry. Many ST employees are contributing to the spec review, and some of them are involved in 2-hour worldwide calls every week. The standard and the rationale behind the standard is well known to ST, which allows us to fine-tune our products for every application. This is a picture of our USB-C with power delivery interface IC portfolio, designed to address most use cases with the appropriate partitioning for source, sync, and dual-role use cases, as well as low and high-powered applications. Today we're going to focus on the sync side applications using the two devices highlighted, including the ST USB 4500 for 5-volt to 20-volt charging applications, and the ST USB 4500L, which supports 5-volt only applications. Rather than discussing the USB power delivery protocol and the standard, the first topic to start with is what you should know at an application level before starting your migration to USB-C. USB-C is no longer a data-only protocol. Thanks to smartphones, legacy USB has become more of a charging protocol than a data one. And today USB-C can deliver up to 100 watts, 20 volts at 5 amps. As Churchill said, where there's great power, there's great responsibility. So migration to USB-C has to be considered from a power management perspective first. Here's an illustration of bad press on the web from a few years ago because of incorrect implementations of early adopters combined with cheap or non-certified USB-C cables. When playing with power without appropriate care, it can be destructive. The same lessons learned for the famous Raspberry Corporation. Believing that migration at 5 volt would make no difference, they originally tried to make it inexpensively using a simple connector swap with some discrete components. In the end, they had to redesign properly, having generated some bad press in between. In addition to Raspberry Pi, there are many other examples having met troubles with past implementations. So why is it a bit more complex than it looks like? Because of the 5 reasons listed here. Because of the swappable connector, you could have a 5-volt 1-amp device plugged into a 20-volt 5-amp device. Likewise, you could have an AC adapter plugged into another AC adapter. And power can be bidirectional, in the case of a roll swap where source and sync devices renegotiate to send power in the other direction. Now those first 3 reasons are operating within the spec, but you also need to plan for devices that are not compliant with the spec in order to protect equipment from damage. And also you need to protect from failed cables and failed equipment that also must be considered. The USB power delivery standard does not include much guidance about protection, but it highlights minimum requirements as listed here, depending on the application role. Note that a device should not rely or trust the attached device to ensure its own protection. ST controllers implement many protection mechanisms which are natively integrated and merged with the protocol and other operational features. Now back to our subject, let's discuss about how to properly implement USB-C as a replacement of DC barrel connectors, custom power plugs, or micro B ports. What a designer must know before starting their first design. While legacy USB was hot socket, with 5-volt power always available on VBus, whether a device is connected or not, USB-C implementation is cold socket on both sides. The source powers VBus only if a sync device is attached and properly identified. A sync device will allow VBus to flow through to the system VIN only if the source is properly identified and the VBus voltage is meeting its power negotiation results. To do so, dedicated active controllers are mandatory on both sides. So we need to consider protecting by default every USB-C port to 20-volt shorts or more, even if the application is only for 5-volt, since not only 5-volt can be available, since voltage is scalable. As shown on the picture, different kinds of 5-volt or higher voltage connectors can be replaced by a single USB-C connector. Implementation will rely on different USB interface ICs or ICs with different settings. Our ST USB 4500L Type-C sync controller can be used to migrate 5-volt connectors to USB-C, while the ST USB 4500 PD sync controller must be used and configured to support any 5-volt to 20-volt applications. The mini dongle shown on this slide is a useful evaluation tool that ST provides. The screw terminals allow for quick prototyping to convert a barrel, an older USB, or a custom power connector to USB-C connector with a limited footprint before it is integrated into the final application. The main controller is called ST USB 4500 and is dedicated to any USB power delivery application up to 20 volt at 5 amp. An important feature that the ST USB 4500 supports is an auto-run capability. Thanks to the integrated state machine, the ST USB 4500 does not require a companion microcontroller, and no software development is necessary. Rather, the ST USB 4500 examines its on-chip NVRAM to determine the target power profiles for the application, and based on the capabilities defined by the PDO profiles, it will negotiate with the source side device to establish a power contract. Although the NVRAM on the ST USB 4500 includes default PDO programming, it can be customized to support any application with only basic know-how about the standard and limited software skills. No need to be an expert at all thanks to the NVRAM programming GUI that ST provides. In addition, we provide example design materials, including schematic, BOM, and open source Altium libraries for layout. Although it's not necessary, thanks again to the auto-run capability, the ST USB 4500 does support an I2C interface and can be controlled or configured by a local microcontroller during runtime. So ST does provide optional software for those applications where more control is warranted or the designer wants to change the configuration on the fly. A spin-off version called ST USB 4500L has been released for pure USB micro B migration, and it's an even more straightforward implementation as the 5-volt optimization is done already by ST with that specific commercial product, so we can say that it's truly plug and play. So let's start with a 5-volt only use case. This slide shows a traditional implementation relying on a legacy protection switch and a discrete USB-C controller, which is operated by an application processor. Among all the functions that must be implemented in order to make it work properly, some, shown here in red, are poorly or simply not implemented in most cases, which results in interoperability or protection issues. In this implementation, discharge and restart management are frequent issues. The ST USB 4500L is designed in mixed signal high voltage technology, so the IC is protected up to 28 volts. Therefore, it can be powered directly on VBus even when the device battery is at 0% and the microcontroller is unpowered. It is able to support dead battery mode, identify a source, check the incoming VBus power, drive the protection switch, and report available current to the microcontroller or directly to the battery charger. It's available in QFN and chip scale package, and it is certified. Such a solution is standalone, plug and play, and requires no software skills or power delivery know-how. In short, here are the features supported. Dead battery support. That means no battery or microcontroller is required to run the ST-USB4500L. It provides safe and ultra-fast power-up. It is powered directly from VBus, so there's zero leakage at all on the application battery, and that extends the battery lifetime of the device. It performs under and over voltage protection, of course, and it implements automatic power budget reporting, which is the duty of the sync device, in order to set the maximum charging current. And especially important, it implements error recovery in order to restart from a fault condition. The key point is that with a ST-USB4500L design, the protection switch is open by default, meaning at the cable attach, and it's closed by the controller only when the electrical conditions are correct. In contrast, using a discrete implementation where a microcontroller must be powered up to negotiate the power contract, that means the protection switches are closed by default and opened only when a fault occurs. And it might close again outside of the USB-C negotiation, leading to interoperability issues. Here in this commented schematic, you can see that implementation requires few components. It is tiny, safe, robust, fast to implement, and certified. The USB-C connector is on the left with the ESD protection shown on the VBus and CC lines. The controller is in the middle, and you can see the discharge paths going into the device. The VBus MOSFET is controlled by the ST-USB4500L in order to pass power through to the rest of the system. And we do show on the lower left of the device the optional I2C interface, although it's not pinned out in this schematic. And there's a signal to drive the battery charger in order to set the maximum charge current based on the power contract that's established with the source device. What the ST-USB4500L brings to your design. The main values are safety and interoperability, which are a must today as USB-C is being largely adopted. A benefit of the ST controller is that it is powered from the USB-C cable and only active when the cable is plugged in, so it enables zero power consumption, which is key for battery-powered devices. Then, because the product is standalone, implementation is straightforward, which is useful for mass-market applications. And also please note the availability of both chip-scale package as well as QFN package types. To support quick implementation, the PCB database is freely available for the dongle evaluation board that I mentioned earlier and is shown again here, to enable fast integration into a larger design. Optional software is available also for an application with an advanced user interface. Again, it's not necessary, but available if the use case warrants more control during runtime. Now looking at higher powered applications, a similar approach can be done for 5 volt to 20 volt applications. And this permits migration to USB-C for applications such as professional drones, smart speakers, power tools, any kinds of toys or robots, personal electronics, personal care devices, and the list goes on. Implementation is very similar to the 5 volt use case, relying mainly on a controller IC with an external protection switch. I had mentioned earlier that the target power profiles are programmed into NVRAM. Although there are default settings, the NVRAM can be customized during manufacturing. That's mainly the method typically used when there's no microcontroller in the design. But another method to customize the operation is to write to internal RAM over the I2C interface without impacting the NVRAM. Again, this allows for more configuration during runtime. For example, the ability to change charging profiles on the fly as controlled by an external application processor on the board. The 5 volt at 3 amp power profile is mandatory by the standard, so that is always the PDO0 profile. But up to 2 custom power profiles can also be configured in NVRAM. That enables support for a custom charger as well as a universal charger. A fully featured evaluation board is also available for convenient hardware and optional software prototyping. With this particular board, you can access the main power path, but we've also included additional FETs, which are controlled by the ST-USB4500 device, and this allows the power to be routed differently depending on which power profile is established. A version of the small footprint dongle with the ST-USB4500 device is also available. All USB-C connectors and passive components, of course, are coming from our partners at Würth, and this is a key point because certification depends not only on the IC, but also on the connector. All tools and collaterals are available online, including one reference design, 2 eval board designs, our software GUI, and a couple of software libraries. As the device is convenient and easy to use, a large community of developers also offer additional boards and software developments on GitHub community, for instance, but also on Tindy, Arduino, SparkFun, and some others. In conclusion, the takeaway from this presentation are to focus on safety first and then interoperability, which are both guaranteed using ST and Würth components. The very compact reference design and the open source collateral are all available online and easily accessible for a very fast implementation. Thank you for your attention. I will now hand this presentation over to my Würth colleagues.
Hello, everyone. My name is Apurva, and I'm a product definition engineer with Würth Electronics. So to continue with our topic of USB Type-C superspeed, in this half of the presentation, we'll exclusively focus on the USB Type-C connectors and cables. So on agenda, we'll start with discussing about the Type-C connector and cable and how their structure is. Then we'll move on to talking about filter and protection components that we have to use in addition to these USB connectors and cables to make the whole design more efficient. And lastly, we'll also talk about some tips and layout measurements and what are like some of the good practices and bad practices that we see in an industry and how can we improve them and make our design more user-friendly. So let's start by talking a little bit about the USB Type-C connector and cable structure. Now here you can see the front view of a Type-C receptacle. So we have D+ and D- pins here that are used for USB 2.0 interface. The TX and RX pins are used for high-speed data such as USB 3.0 or for any other alternate modes. Also, we have some configuration channels such as CC1, CC2, and SDU1, SDU2 here. Now, what these channels are doing, they are making the connector configurable for low-speed data lines if you are going to use the connector for some alternate modes. Making this connector a very customizable one and a very flexible one so that it changes with different types of operation. And that is why these type of connectors can also be used in very unconventional industries such as audio. Now, similar to the receptacle, we also have front view of the USB plug. If you notice the difference here, this is a 22-pin plug versus a 24-pin receptacle. If you see, the B6 and B7 pins are missing. The B6, B7 pins, if we want to implement them with the differential D- and D+ pins, what happens is we are essentially creating a short circuit. And with this, we might not be able to transfer the data through this connector. That is why usually these B6 and D7 pins are not connected or not circuited at all. But nowadays, with newer connectors coming up, you'll notice that all these plugs, they come with 24 pins. Now, what do they do in this case? They just add like a small multiplexer IC behind this connector, which can help us to divide the signal, making it possible to use this connector even with 24 pins or the added 2 extra pins. Now, when it comes to the electrical specs of USB connectors, we have some standards defined to design these numbers or to come to these numbers. For contact quality values, for example, all the measurements are done at 20 millivolts and 100 milliamps. Maximum value for all contact resistance is 30 milliohms. Now, this value remains same even after all the environmental tests are done. So the contact quality is always ensured in a new state even after all the tests are conducted. 100 milliohms resistance is the minimum necessary insulation between these adjacent contacts. And the maximum dielectric withstand voltage given by the standards is 100 volt RMS run during 1 minute of time frame. Now, the USB Type-C 3.1 is given for a working voltage of 20 volts and a dielectric voltage of 100 volts. Although the real breakdown voltage could go as high as 1000 volts. Now, the zoomed in picture over to the right shows a little bit of carbon traces in between the adjacent contacts. Now, these traces are created because the connector was exposed to higher voltage, closer to breakdown voltage. So if we keep on continuing to give 1000 volts to the connector, we'll see such meltdowns and such carbon traces between the adjacent contacts. Now, usually these traces are very small and hard to see through naked eye. And the material here used is not at all flammable, but of course it is not recommended to use your connector beyond its breakdown point. Now, this slide explains the current rating test for Type C connector and its thermal behavior. Measurements in this case are either done with a thermocouple glued onto the connector, or we can simply use a thermal camera to see the temperature rise. With this setup, we can measure the temperature rise of three things: the connector, USB cable, and of course the PCB. If you see the graph, the temperature rise for all these three components is way below 30 Kelvin, which is the recommended standard value. Cable usually has a lower temperature compared to the connector, and the PCB is always designed in a way to give lower temperature than the connector as well. The reason for this being, when higher voltage is applied to the connector, it has a tendency to get warmer, and after a point it needs certain scope or certain margin to dissipate that energy in the form of heat, which it does through a lower or a cooler PCB compared to the connector temperature. A small point to note here is all these temperatures are values for the external part of the connector. So it is very difficult to do measurements on the internal pins. But of course, we can generalize and assume that the inside of the connector is going to be way more warmer than the external surface. Moving on to the mechanical parameters. The first one that we have is insertion extraction value. The goal of this test is to check that all the components show same range of effort needed for insertion and extraction of the connector. This is to make sure that the final customer will always need the same amount of force, no matter what USB connector he is using. That means irrespective of any brand, the effort or the force needed to insert the connector in or getting it out should be the same. And of course, these values can change, especially the extraction value, due to the regular wear and tear of the plug and the receptacle. So according to standards, the insertion force should be between 5 to 20 newtons, extraction between 8 to 20 newtons. But after 10,000 cycles, this initial extraction value can drop from 8 to 6. Second type of mechanical test is to check the durability of the connector. Now, this test is conducted without applying any load, which means there is no voltage or current applied to it. Standard values are for 10,000 cycles. And a good result is assured by small tweaking or small adjustment in the value of contact resistance. So if you keep the contact resistance between 40 milliohms and 50 milliohms, that is considered to be the best and the common measurement value to test your connector for its proper working for power and data. Now, a good quality or a powerful Type C receptacle plus connector can hold up to 1 liter of water. So that itself speaks a lot about the durability of these small connectors, these small receptacle and plugs, if they can hold this heavy of a component. Now, these values are very, very critical for the V bus and ground pin, because that is where the highest power and highest current gets accumulated. So with our quality of connectors, it can very well handle up to 30,000 cycles of matting, which is more than enough for most of the applications. But after 30,000, here you can see that there is like a gradual increase in contact resistance, which means that because of this increase, there is going to be more heating of the component. But for most of the applications, 30,000 matting cycles is a good number, and this USB connector performs very well up until 30,000. So when it comes to shielding, external shielding for plug is done with a single tube that creates better mechanical holding and limits the possibility to break it open. 4-point shielding between receptacle and plug is recommended by the USB standards. And the shielding material that we use is a very high quality steel. Steel is considered to be a very efficient material and one of the best for mechanical holding. And that is why this kind of a material is preferred while designing a USB plug and receptacle. All the 4 points are required for shielding according to the guideline. We provide 6 points or sometimes even more to provide a better stability and better shielding. The more contacts you have, obviously, the better shielding can be assured. Now that we know the construction aspect of these USB connectors, we can move on to a topic of filter design that is needed in addition to these connectors to make our system or make our design more effective. So some customers are still using USB 2.0. The reason being that they don't necessarily require more speed. But of course, the industry is moving on to faster and faster speeds. And with that, we need to modify or tweak our older design. Now, in our experience, we see a lot of customer designs like this, which have small, minute mistakes, which could be harmful for higher speeds. So usually USB has a differential impedance of 90 ohms. And with all the routings that are marked here, the system has a tendency to, or it has a little bit of difficulty to maintain this impedance of 90 ohms. Luckily, with USB 2.0, even with 480 megabits, is low enough to guarantee you the function, and it mostly works very well with these type of slightly bad design. But when it comes to USB 3.0 and when we have more speed, these designs are not valid anymore. And at high speed design, the data loss becomes very high for such kind of circuits, and that is why we need more efficient filter design around them. To give you a mathematical example, we'll consider 2.0, which has a speed of 480 megabits per second, and the system impedance is 90 ohms. So with this maximum speed, we can now have a fundamental frequency of half of it, which is 240 megahertz, and the wavelength will be 120 centimeters. Now, the rule is not accurate, but there is a good rule of thumb in terms of EMC and in terms of data signal that the impedance transformation below 1/10 of the wavelength is considered to be negligible. So in this case, every structural length of PCB on the cable and the connector that is below 12 centimeters is usually not very critical for the data signal. And therefore, you can violate this requirement of 90 ohms very heavily in these cases. So when it comes to 2.0, it is not a very hard and fast requirement to maintain the 90 ohms of impedance. Everything over 12 centimeters could be a problem. It must not always be that way, but it could create problems depending on the environment and the application. But when it comes to USB 3.0, with the speeds in the range of 5 gigabits per second, we have a critical length as small as 12 millimeter. And 12 millimeter is pretty short when we sum up all the components on the PCB trace, such as the cable, the plug, the filter components. There is very little scope to tweak this 12 millimeter length. And that is why if we go a little bit plus, like we say, if we just take 14 millimeter, it could also give us like a lot of data loss. And that is why designing USB 3.0 becomes very, very critical, and we need to take a lot of precautions designing a PCB for such higher speeds. So for example, if you have a PCB where you have to route high-speed layers on both the top and the bottom layers, it could be anything such as USB or HDMI or even like a 10 gigabit Ethernet. If we have any of these high speeds on both ends of PCB, we need to have at least 6 layers of this PCB. Only with 6 layers, it is guaranteed that every data signal has a designed ground return path on the same distance to guarantee the same impedance. So when we have 6 layers, the distance between this high-speed layer from the top and ground is same as we have it at the bottom. If we have a 4-layer PCB and we have VCC and ground in between, the distance from top to ground and bottom to ground is completely different, and that could cause a mismatching in our capacitive coupling. To get also a very good power integrity in the system, it is recommended that the ground should be at 100 micrometers max distance from the VCC, so that we have a good capacitive coupling. It is not too high or not too low, and that is to assure that we have best of decoupling, best of EMC and signal integrity in our system. Okay. Now here we have created a dongle for 5 to 10 gigabits per second. We show here that it's critical to have filter components and protection components such as common mode chokes on this side, ESD protection on this side, as well as some filter components such as inductor and ferrite beads for our power path. So to test this, we have an analyzer with differential impedance of 100 ohms. Since it is 100 ohms, dividing 90 ohms is impossible in this case. So you can either do 50 ohms single-ended or 100 ohms differential. Therefore, we made a 100 ohm differential adapter. Now, in between the cable and the adapter, we'll plug in this dongle and measure the specs. Then you can see the influence of all these added components on the design. And we can see how this eye diagram or how the signal diagram changes or remains the same, depending on what type of components we are adding in between this plug and the receptacle. So what all things do we need for this USB 2.0 and 3.0 legacy? We have ESD protection and common mode chokes for USB 2.0 side. Similarly, we also have common mode chokes and ESD protection for high speed such as USB 3.0. And we have power filters and ESD for the power path in between plug and the receptacle. Here in this slide, we can see the overview of the dongle and what type of components are used within these dongles. The yellow one we have for low speed lines and control signal here, and the blue one is for high speed such as USB 3.0. And at the bottom, we have 100-watt power path with 20 volts and 5 amps. Of course, for the super speed lines, we need special high frequency common mode chokes, which have very, very low strain inductance. For low speeds, we do not necessarily need high frequency common mode chokes. But for ESD protections, we need very, very low capacitance paths, which can be as low as 0.05 picofarad channel to channel capacitance. And the power path, we have inductors and ferrite beads. Ferrite beads are used for filtering for frequencies above 10 megahertz, and the inductor is used to filter out any noise below 10 megahertz. So what is important when we look at a common mode choke? We have graphs such as insertion loss versus the frequency. Now, in this common mode choke, which is a high frequency one, we see that we have 3 dB of insertion loss at a very high frequency of 10 gigahertz, which is, according to USB standard, considered to be very, very low loss. And that is why these type of high frequency chokes are used for high speed. Next, for ESD protection, we use TVS diode, which in this graph shows that it has insertion loss as low as 1.5 at a high frequency of 10 gigahertz. And then lastly, we have a bigger TVS diode, which has the insertion loss of 3 dB at 7 megahertz, which is also not considered to be bad according to the USD standards. So let's see what happens when we put a regular common mode choke, which was intended for 2.0 speed, into a higher frequency such as USB 3.0 specification. Now, in this eye diagram, in the first one, we can see that we have very high strain inductance, which means that this rising edge and falling edge of the signal are too slow because there is like a lot of inductance present on it. When you use a high frequency component, which are more suitable for higher speed designs, you'll see that we have enough slope for the rising and the falling edge, and the signal is not at all disturbed by addition of these components. So that is why it is important to select the common mode choke in accordance with what speeds we are trying to achieve and what frequency we are working at. When it comes to thermal behavior, obviously the inductor is of course the hottest point. It is the part with highest RDC, and that is why the heating is more. That is why a lot of heat dissipation is necessary around this inductor. One easy way to reduce the heating or to lowering the RDC is to just go with a little bit of higher package of inductor or increasing the PCB a little bit so that it gives space to dissipate the energy in the form of heat. Now, in the next few slides, we will try to see how we can maintain the signal diagram or how we can maintain the eye diagram by addition of common mode chokes or ESD components. So when we add all these components, it becomes important not to harm the signal or not to manipulate the signal. So now we'll compare in next few slides what happens when we have like an empty PCB where there is only plug and the receptacle and no components are added, and what happens when we add more components into it. So initially, when there are no ESD protection components or no filter components, we have the fixture, which is around 100 ohms, which is as expected. Then we also see the influence of impedance due to plug, which is around, it's not exact, but around 90 ohms. Then we have the PCB itself, which has impedance of 100 ohms, and the receptacle similar to the plug, which is around 90 ohms. And lastly, the cable, which is initially below 90 ohms, but eventually it settles down at 90. So the eye diagram without any other components added is perfectly good. Here we can see the slopes are good and the eye diagram is very good for the signal transfer. Now here we'll insert the common mode choke. And with the addition of common mode choke and the proper common mode choke depending on the speed, we can see that the fixture is still pretty much the same. There is a little bit of difference around this cable due to the added stray inductance. Plug stays the same. It is still close to 90 ohms. The common mode choke, it made it little closer to 90 ohms with slight difference due to the stray inductance of the choke. The PCB remains the same and receptacle also remains pretty close to 90 ohms. So when we selected proper common mode choke, proper filter, we see that the eye diagram or the signal diagram is not at all manipulated or not at all changed. Now in the third stage, we also added the ESD components here. And we can again see that the fixture still remains the same. PCB is also close to 90. Common mode choke also didn't change its functionality. PCB remained the same, as well as the receptacle is the same. So that assures us that the ESD protection components that we have selected are not changing or manipulating the signal at all. And lastly, what we see is that these micro stripes, so far we saw that they were not coated with anything or there was no layer of protection applied over that. The reason is like the protection coating will also have some kind of epsilon R, which can manipulate the functionality of the signal. But in case if we put that coating also on it, proper type of coating to make sure that the fixture, plug, common mode choke and receptacle impedances still remain the same and the eye diagram is not manipulated at all. So whenever we are adding the components on the grounds of protection, on the grounds of safety, we always need to make sure that they don't change the eye diagram, they don't manipulate the signal transfer or the data transfer. Now, all these things that we did so far with the dongle were for 5 gigabits per second. But even if the speed is higher to, let's say, 10 gigabits per second, the same type of structure or the same type of components can be used only with an addition of an USB equalizer. And nowadays, pretty much every chip that USB uses has an USB equalizer inbuilt in it. So this helps to adapt the signal to the cable length. And even then, the eye diagram will not be hampered or not be manipulated even at higher speeds, such as 10 gigabits per second. And coming to the end of our presentation, we have a very functional and then very effective development kit of 100 watts with ST. So if you want to experiment with USB Type-C content, if you want to experiment with Type-C panels, definitely go and check this kit out. It has a lot of functions and you can experiment a lot and learn a lot about USB Type-C. And that is it for me. Thank you all for listening. And I would also like to thank Jeff and ST for such a good collaboration on this webinar. And in the next half, we'll take some of the questions to me. Thank you.
Okay, we do have a few questions coming in here, and we have Jeff Hallio, who was our presenter. We also have Quentin Ledbeer answering questions at the end. Our first question, I believe, actually goes to Jeff. Is the ST-USB 45000L a suitable device for converting USB 2.0 OTG devices to USB Type-C OTG mode applications?
Yes, it should be. The ST-USB 4500 really is only involved in the power delivery side. So based on the schematic that was shown in the presentation, really only a subset of the pins are used for the power delivery negotiation. So we have the CC1 and the CC2 pins, as well as VBus and ground. So it's really a subset of signals that we look at for the power delivery. When it comes to the data side and the on-the-go, where you have the source and the sync devices negotiating, more on the data side, I believe, and which one, or rather exchanging device IDs and things like that. That's all going to happen, I think, outside of our device itself. So there'll be a data controller running in parallel with our power delivery controller. I believe the OTG would actually more involve the data controller side. And typically that's integrated into the microcontroller or an applications processor. So the 4500 is really just involved with negotiating the power delivery contract between the source and the sink. I think the other stuff, and in particular the OTG negotiation, is going to happen outside of that.
Thank you very much, Jeff, for answering our question. This next one I also believe goes to you. This person has read that a USB PD source needs to advertise whether it also works as a data DFP or is it dataless. What does the sink do with this information? And what if they use a PD controller that advertises no data, but still try to send data through an autonomous MCU? Are they still able to send that data?
Okay, sure. I'm not exactly sure about this question, and I think I'm actually going to refer to my last answer as well, which is this sounds as though it's going outside of the scope of what the ST-USB 4500 is meant to negotiate. You know, we're really just on the power delivery side. When we talk about downward-facing ports and whether or not a port is data or dataless, I think that's going to involve the data, or rather the data controller for that port, which again is going to be integrated into the microcontroller or the applications processor.
Okay, I hope that we were able to answer that question thoroughly. Just a reminder, if your questions do not get answered or we want to go more into detail, you can always reply to our follow-up email from here for you at we-online.com. You can also email me, amelia.thompson@we-online.com. Our next question, we believe, is going to Quentin. What kind of conducted emissions limits are there for USB-C power sources? They are referring to conducted emissions on the DC USB cable side.
Correct. So thank you for the question. Actually, I believe that the emission limits are actually linked to the field of application that you're planning to implement your USB solution. So it will really depend on whether you're into the medical field, consumer field, or industrial field. And NORM is going to give you different limits to which you can not exceed on your emission and conducted emissions.
Thank you very much, Quentin. Our next question here, do you see many real applications using USB 3.0 with PPS? I believe that this might go to Jeff, but Jeff, you can correct me if I'm wrong.
Sure. Yeah, so with PPS, the programmable power supply, and I've the name of that spec from Qualcomm and their branded version actually escapes me now. I think it's Quick Charge. We do see that happen. That's really more on the source side, I believe, where we would have to pass through a different voltage on the V-bus. But yes, so I guess the short answer to that is we do support PPS. However, not the branded quick charge version, which I guess is the Qualcomm specific. I haven't necessarily been involved personally with a lot of those designs. More often than not, the ST-USB 4500L or the 4500 is integrated with a device of some kind that is specifically looking for a certain power contract to be able to charge its battery. And what those devices are doing and what the power profiles that are programmed into NVRAM on versus the source side, they're going to, during the negotiation, try and choose the highest power profile that both sides support. If you look at the state machine that's implemented on those parts, and actually the spec as well, there is a decision tree whereby both ends will agree, okay, this is the highest power profile that we both support, let's use that. So more often than not, that is the application that I've been involved with versus programmable power supply, where it's changing on the fly. Not that you can't do that, certainly, and that might be one of the applications where we use the I2C to be able to change the configuration of the ST-USB 4500 on the fly. So in that case, you might need a microcontroller external that could write to the memory and then force a renegotiation with the source side. That might be how PPS would be implemented with this particular device.
Excellent. We have a time for a few more questions here. Our next question is: a chip-equipped cable required to enable 100-watt PD? Quentin, I believe that question goes to you. I could be wrong again.
Yes, absolutely. So most of the cables used for high frequency, if you want both to have the high frequency data, 5 gigabytes or 10 gigabytes, and on top of that you want to have the power, then definitely you need to have the passive implemented into the cable as well. However, if you just want the 100 watts and you don't want the communication, then in this case you could use any cable that's rated for the current and voltage that support 100 watts, so 20 volts and 5.
Our next question here: what is the difference between USB-C source and USB-C sync?
Sure. So USB-C source is going to be the device that is driving V-bus and putting a voltage and providing the power. Sync device is accepting the power. That's your phone if you're charging it, or some other small IoT device that has a battery, for example, and is accepting the power. That's the sync side. So the ST-USB 4500L and the 4500 are both sync devices. ST also has the ST-USB 4710, which is a source-only device that very similarly acts with this auto-run state machine. And then we have the ST-USB 1602, which can do a dual role and can act as either source or sync, although that part does require an external microcontroller. That's a bit more complicated to do the dual role, so we're not able to do that in a fixed state machine.
All right, Jeff, I believe we have another question here for you. Do the CC1 and CC2 pins determine how the orientation of the cable?
Yes, that's exactly it. And so on our our device to be identified as a sink, there's actually a pull down on the CC1 and the CC2 lines. On the source side, there's a pull up to VCC. So both sides are able to detect, well, I should say the source side is able to detect a cable insertion when it's pulled to ground. I didn't get into this detail in the presentation, but based on the value of that pull down resistor, it can also provide some information about both sides, what the sink is able to provide by default for current capabilities, and also the sink, and provide some insight into the sink side. But only based on the cable orientation, only one of those will be pulled low on the sink side and high on the source side.
We have time for a couple more questions here, and I think the last couple are going to Jeff. Our first question, as presented for charging, there is USB negotiation done at the beginning. Are there any data blocking features being implemented to use with public or hotel or airport chargers with USB-C receptacle or even USB-C plugs? It appears that simple hardware disconnect of data lines would interfere with the initial USB negotiation needed for proper charging setup.
Yeah, that's a great question. I'm always a little nervous plugging my phone into USB ports at the airport as well. But the actual negotiation for the power delivery happens over the CC lines. Just to go into a little more detail, the cable gets inserted. We're able to detect the orientation of the cable on those CC lines based on the pull-up. But then there's a modulation scheme that happens between the source and the sink, and that negotiation happens over the CC lines themselves. The USB data lines, the DM and DP lines for USB 2.0, or the super speed, higher speed differential lines, those are not involved with the actual power negotiation. So from our device, nothing goes beyond our part. The CC lines are terminated there, and there's no data shared with the port that you're plugging into. So if there are some data blocking features, again, we would need to implement those on the data controller path, or wherever those USB 2.0 or the super speed data lines are routed to.
And our final question, which is a great one to end on, are there PDF files of the footprints for the USB connector with the ST-USB 4500 QFN package?
I would have to check to see if there's PDF. I do know we provide layout. I want to say they're in Allegro, but I can't recall the format that we use. I'm sure that we could provide PDF versions of those to our customers if needed, though.
Absolutely. And thank you, everybody, for joining us for today's Würth Electronic webinar. Huge thank you to Jeff Hallio, Quentin Letibier, and Apurva Engel for presenting and answering all of our questions at the end. As a reminder, don't forget to register for our next webinar. It's a behind-the-scenes look at current sense resistors, powered by Digi-Key Electronics, the exclusive sponsor of all Würth Electronic webinars. You can also hear most of our presentations in an audio format. That's right, we have our Würth Electronic What's Up radio podcast, where each week we are bringing our technical information to a strictly audio format. You can find us on Spotify, iTunes, and everywhere. I'm Amelia Thompson, your host of the webinars, and I'm hoping to see you again tomorrow. Have a great day.